Hey folks, welcome to this episode on types of reactions. So we have 6 main types of reactions: synthesis, decomposition, single displacement, double displacement. We also have neutralization, which is kind of a subcategory of double displacement. It's just a specific acid-base reaction. We have combustion, and finally we have a redox reaction, which we'll briefly look at right now, but not really take too much time into. So why do we care about these types of reactions? Well, we can understand our observations a little bit more, but what we're trying to look towards and trying to do is predict our products of these unknown reactions. So if we add this and this, what will we get? So the first type of reaction is synthesis reaction, and it's a combination of atoms or smaller molecules that form a larger molecule. So in this case, we have one reactant plus another reactant, in the case A and B, and we create one compound AB. So if we look at this, here's some examples here. We have zinc and sulfur to form zinc sulfide. Well, zinc is Zn, sulfur is S. To figure out what our formula here, we have to use our ionic formula rules. So we have Zn and S. This is 2 plus, this is 2 minus, because in group 6 and zinc, we just know that it's going to be 2 plus, so we cross, and we get Z and S as the subscripts cancel out. So that's a very simple example of a synthesis reaction with two basic elements. We can also have small molecules, where in this case we have hydrogen chloride, HCl, and we have ammonia, which is NH3. And when we add these together, we actually get ammonium chloride, which is NH4Cl. And again, we can figure that out, NH4Cl. This is 1 plus, this is 1 minus, cross, we get NH4Cl. Second type is a decomposition. It's just the opposite of an addition reaction or a synthesis reaction, where we have when we go from one reactant into two basic products. So again, here we're splitting up from AB into A plus B. So again, if we have a binary compound, meaning that it's just made up of two elements, they're going to break down into their basic elements. So here we have water, which is H2O, and we have two basic elements. We have hydrogen and we have oxygen. So it's going to break up into H and O. Now remember that these are diatomic, so it's going to be H2 and O2. We're going to have to balance this, and we'll talk about this a little bit later, but we'll just briefly do that right now. We're going to have to balance this and do something like that, and that's the law of conservation of mass. So if you're not there yet, don't worry, we're going to talk about balancing in a little bit. Ammonium nitrates, we have NH4, NH4NO3, and again, the way I got that, I have NH4 and then NO3, I know nitrate, this is 1 plus, this is 1 minus, cross, we get NH4NO3. In this case, nitrous oxide, so we get N2O and water. Okay, so we'll be able to balance that as well if we need to. Now, some of the exceptions for decomposition are carbonates, and these don't break up into the way that we think they are. They actually break up in a different format. They break up into carbon dioxide and a metal oxide. So metal oxide is just some kind of metal with some oxygen. Now again, you have to use your ionic rules to create this formula. So let's look at CaCO3. This is calcium carbonate. So this will break up into CO2, so we're going to form that CO2 gas. And then we'll have to create some kind of metal oxide. Well, what's the metal that's left over? Well, we have calcium. So calcium is going to react with oxygen. We have 2 plus, 2 minus, because this is in group number 2, and this is in group number 6, so it's going to lose and gain. Again, we cross, and we get CaO. So in this case, it's already balanced. We don't really have to do anything. But again, when you look at these carbonates, they break up into CO2 and a metal oxide. There are other exceptions, but we're not going to be talking about them in this course. You will be learning about them a little bit later. We have single displacement, where one element displaces another element in a compound. Now, it's really important to figure out whether or not that single element is a metal or a non-metal, because metals replace metals and non-metals replace non-metals. So in this first example, here we have A, and A is that first puzzle piece. The first puzzle piece in the name is always the metal, or like zinc oxide or sodium phosphate, whatever. That first element is a metal. So we know that this is going to be replaced by this, which means that they both have to be metals. On the second example, here we have D, which is going to be the second part of this name. And because it's the second part of the name, we know it's a non-metal, so a non-metal will have to replace a non-metal. So again, here we have a metal. It has to replace this metal to get this, this kind of replacement reaction. And we know that this is a non-metal. We can say maybe it's like H2 or O2, something like that. And it's going to replace this non-metal to get this compound over here. So in here we have metals replace metals. Magnesium and silver nitrate. Well, we're going to write Mg over here, and silver nitrate, which is AgNO3. I'm sure you can figure that out. Now, here what we're looking at is this is a metal, so it's going to replace the other metal. So what should we get? Well, let's just write out a name here. We should be getting silver by itself because the magnesium is going to displace the silver, and we should get magnesium nitrate. Okay, so I'm just going to write the symbols here. I know that the symbol is just simply Ag. What's the formula for magnesium nitrate? Well, it's Mg and NO3. Mg is 2 plus, nitrate is 1 minus. We cross, and we get Mg bracket NO3 2. To balance this, we just add a 2 here and a 2 over there. Non-metal replaces non-metal. So here we have bromine and calcium iodide. So bromine, remember, is the diatomic molecule, so it's going to be Br2. And calcium iodide, well, that's going to be CaI2. This is 2 plus, this is 1 minus, cross, and we get CaI2. So when bromine replaces one of these elements, well, first of all, we have to figure out which element it replaces. It's a nonmetal, so it's going to replace the nonmetal. It's going to replace the iodide or the iodine. You're going to get iodine by itself. So we'll have iodine. It's not iodide anymore. We only change that ending when it's in a compound. Plus calcium bromide. So what is the formula for iodine by itself? Well, but again, it's diatomic, so it's I2. And what's the formula for calcium bromide? Well, we have CaBr, all right? It's just by itself until we figure out what the charges are. 2 plus, 1 minus, we cross, and we get CaBr2. Okay? Now, just one note. Here we have I2 and we have Br2. It's not because that they are diatomic that they exist as Br2 here or I2 here. It's because of the charge balancing from the calcium. The calcium charge was 2 plus, so we brought it down there. And here, yes, they exist as a diatomic molecule because they are diatomic. But here, this is only by happenstance. If this was to be bonding with aluminum, for example, this would be I3. Double displacement is when we have elements, again, replacing other elements in compounds. So there's no lone elements. There's a compound and a compound, resulting in a compound and a compound. Now, you have to pick one. Either you replace the metals with the metals or the nonmetals with the nonmetals. If you replace both, well, you get the same thing. Okay, so in this case, we're just going to replace the nonmetals with the nonmetals. So here we have B and D, and you can notice that they switch places, D and B. So in this case, we have silver chloride and silver nitrate. Well, we're going to switch the nonmetals, so I'm just going to write out the metals. Here we have sodium, and that's going to switch with the silver nitrate, so it's going to be sodium nitrate. And we are going to get silver, we leave that in place, and we get silver chloride. So now that we have the kind of word equation, we should figure out what that looks like. Well, sodium chloride, this is NaCl, this is 1 plus, this is 1 minus, cross, and we get NaCl. Silver nitrate, this is Ag and NO3. This is 1 plus, this is 1 minus, we cross, and we get AgNO3. Sodium nitrate, we have Na and NO3, 1 plus, 1 minus, cross, we get NaNO3. And silver chloride, Ag and Cl, 1 plus, 1 minus, cross, we get AgCl. So if we look at this is all balanced. That's our double displacement reaction. Now, a subset of double displacement reaction is neutralization reaction, where an acid and base form products that have a pH that are closer to 7 than either of the reactants. Remember, an acid has a lower pH from 0 to 6.9, really, and a base has something greater than 7, 7.1 to 14, for example. We create an ionic compound, which is just called a salt, and then we also create water. So how do we create water? And this is the interesting part. Let's say, for example, we had HCl acid, aqueous, reacting with NaOH, aqueous. So when they form into water, they split up into their ions, the H and the Cl, the Na and the OH. So what happens is that the result, what is going to be the result? Well, we have to form a salt and we have to form water. How does the water form? Well, here we have our H from our HCl, and here we have our OH from our NaOH, and we create this water. Now, what happens to these leftover ions? Well, let's see what happens when we put them together. NaCl, aqueous. We have just formed a salt. So we use these two to form our salt, and we use these two over here to form our water. So these are just some common acids and bases that you should know, so you can print this out and have it for your storage. Remember that we've actually gone through how to name these various acids. Okay, remember that if it's an ic, then that the prefix of the oxyanion was 8. If it's os, which we don't really have any in this list, that prefix of the oxyanion was ite. Our sixth reaction is combustion reaction. This is when something reacts with oxygen to produce oxides. Now, the oxides that we have produced are oxides of carbon and oxides of hydrogen, and the way that they look are carbon dioxide and water for a complete combustion reaction. We might also form other oxides, for example, carbon monoxide, when we have incomplete combustion, but this is what we're trying to tend to. Having an exact ratio of oxygen to fuel to produce only carbon dioxide and water. Now we do produce energy. Sometimes it's included as part of the formula, sometimes not. But this energy is just transmitted and released as heat and light. So in this case, we have a complete combustion. We have fuel. Again, O2 reacts to form CO2 and H2O. The beauty about complete combustion reactions is that this part of the reaction is always going to be the same. It only depends on the fuel as to how we're going to actually balance. So in this case, we have butane, which is C4H10, okay? And we have oxygen, CO2, and H2O. Okay, so when it comes down to balancing this, we can look at this. Let's see, we have 2, 5, that's not going to work. We're going to have to double this up. We're going to have to put a little 2 there. Oops. C4. Put a 2. Slide over a little bit. We have a 2 there. So that means we have 8 over here. And then we're going to have 10 over here. Now how many oxygens do we have? We have 16 plus 10. That means we have 26. So this is going to be 13. Okay. In incomplete combustion, which we're not really going to be looking at too much, we have the hydrocarbon, which is our fuel, plus oxygen. But what the difference is between here and here is that the ratio to oxygen to fuel is not precise. It's not exact. There is depending on what the actual fuel is, you're going to need a certain amount of oxygen atoms for every molecule of fuel. In this case, if, for example, we're using butane and oxygen, here we need 13 oxygen molecules for every 2 molecules of butane. But in incomplete combustion, maybe we'll still have 2 molecules of butane, but we'll only have 7 molecules of oxygens for those 2 molecules of butane. That's not the proper ratio, and so what we're going to do is we're going to be creating other compounds as well, like carbon monoxide and carbon. So here's just a general list of the types of chemical reactions and their general formulas. The last type is a redox reaction, which is called reduction oxidation, and this involves the transfer of electrons from a reducing agent to an oxidizing agent. So oxidation we just call it based on the loss of electrons, and when something gains electrons, we say that it's reduced or it undergoes reduction. A reducing agent is something that is oxidized, so it actually readily donates electrons to another substance, and it causes the other substance to become reduced. That means the other substance gains electrons. Now, if it loses electrons, that means it gets oxidized. Okay? An oxidizing agent, however, forces the other substance to lose its electrons, thereby gaining those lost electrons. By gaining those lost electrons, it gets reduced, and there we go, our little circle of life there. So in this case, this kind of explains it a little bit better. So reducing agent is oxidized, and that means that it's going to lose its electrons and give its electrons to the oxidizing agent, which in turn gets reduced. This is something you're going to be exploring more in grade 12 when it comes down to electrochemistry, but just to give you an idea of what that 7th reaction is. That's it for this one. Thanks very much for watching. See you soon.